Hello everybody, welcome to our virtual labs for 2020. Today we're going to start with an experiment in which we're going to determine the properties of a fluid, and we're going to be using an interesting experimental setup to do so. Casey.
So you can tell a lot about a fluid and its properties from the way that it interacts with other objects. The case we'll be considering today involves a sphere. So if you think about flow from the left side of the screen towards the right side of the screen at pretty high speeds, you may see something like this, where the flow begins contouring around the sphere, but then detaches to form this vertical wake. Anyone that's tailed behind a semi on the freeway is familiar with sort of wake structure. At much slower speeds, though, you have something that looks a little different, where the flow, again, moving from left to right, encounters the sphere, contours around, but instead of detaching, will actually follow all the way around and resume its path on the other side of the sphere. We can demonstrate this phenomenon using a candle and a stream of air on opposite sides of a cylinder. Even though the cylinder is interposed between the stream of air and the flame, the air is able to contour around and blow out the candle.
So what we can do is now design an experiment where we know how a sphere is moving through a fluid and look at the forces that are acting on the sphere as it moves through the fluid. The sum of forces, if the sphere is moving at constant velocity, the sum of forces acting on the sphere are going to equal 0. The forces acting on the sphere in this case will be the weight of the sphere, the buoyant force, because it's immersed on the fluid, and the drag force, which is the force acting on the surface of the sphere.
So we can design an experiment now where we have a sphere, the diameter of which we've measured, so we can determine its size, and with a known material, therefore a known material density, that is dropped into a fluid with unknown properties, rho f and nu f, these being density and kinematic viscosity, and we measure the terminal velocity of this sphere, which allows us then to write out explicitly what each of these forces are.
So here, each one of the forces can be calculated. The weight of the sphere can be calculated using the specific weight of the material that we're using, multiplied by the volume of the sphere. The second force is the buoyant force that, as we learned in our fluid class, is proportional to the volume of fluid that gets displaced. So in this case, the buoyant force is equal to the specific weight of the fluid multiplied by the volume of the fluid.
And then finally we have the drag force, which comes from a very special case, which is known as Stokes flow. In this particular situation where the sphere is drifting very slowly through a fluid, then the drag due to the viscosity of the fluid can be calculated as 3 pi times the terminal velocity multiplied by the diameter of the sphere and the kinematic viscosity and the density of the fluid. This isn't the case for every condition with a sphere falling through a fluid, but for this particular experiment, this is the applicable expression.
So we can take the 3 forces, add them together, and they should equal to 0. And when they do, rearrange with a little bit of algebra, we can come up with an expression that relates the viscosity of the fluid to the diameter of the sphere, the gravitational constant, and the ratio of the densities between the fluid and the sphere.
The problem here is we don't know the fluid density. This is because we started out with 2 unknowns and we only performed 1 experiment. To resolve both unknowns, the kinematic viscosity of the fluid and the fluid's density, we need a second set of experiments. So we designed the experiment with 2 differently sized spheres, D1 and D2, potentially made of different materials with densities ρ1 and ρ2, and we time independently their respective terminal velocities, which may be different. This allows us to get two independent estimates of the viscosity that, when set equal to each other, allow us to solve for the density.
So then we end up with an expression that gives us the density of the fluid as a function of the variables that we measure for the two experiments, with spheres that have different diameters, that have different densities, labeled here as density 1 and density 2, and corresponding different terminal velocities there.
So with this second expression in hand, we can now calculate both the fluid density and the fluid's kinematic viscosity, shown here. These two expressions then form the basis of what will be the data reduction equations in the experiment we're about to demonstrate.
All right, so with this knowledge at hand, we can move on to perform the actual experiment. We'll start our experiment today describing the different elements and measurement devices that we're going to use to perform it. Casey?
So laid out on the table in front of me are the different instruments we'll be using in our viscosity and density experiment. They consist of a standard set of calipers, a stopwatch, a linear rule, of course our set of spheres that we'll be testing, and of course the experimental setup behind me, which is a circular tube filled with glycerin that's equipped with a gate at the top that allows us to open it and allow a sphere to begin falling, as well as upper and lower lines scribed into the tube so that we can time how long it takes the sphere to descend a known distance so we can find its terminal velocity.
So we will be using, for these experiments, two different kinds of spheres. One of them is a small one, but it's made of steel. The other bigger ones are made out of Teflon. In addition, we're going to keep track of the temperature in the room. We're going to be using these two thermometers. As we learned in our fluid mechanics class, room temperature will affect the viscosity and the density of the fluid that we're investigating. So let's start the procedure. So the first thing I'm going to do is measure the temperature of the glycerin. So I have 23.3 degrees centigrade. Let's go ahead.
The next step is to use our linear rule to measure the distance from the top scribed line to the lower scribed line, which I get at 60.7 centimeters.
Perfect. Our next step is going to be measuring the diameter of each one of our Teflon balls that we're going to be dumping. For that, I'm going to be using the caliper. And I'm measuring a diameter of 6.32. Okay. Next, I'm going to drop our ball into the glycerin.
Now at this point, the sphere is sitting on top of a gate, which Ricardo will be able to rotate out of the way, allowing it to fall freely through the glycerin, at which point I'll begin timing.
Are you ready to time?
I'm ready.
All right. Here you go.
Past the first mark. Now at this point, the buoyant forces, the weight of the sphere, and the viscous friction forces are all in equilibrium, so the sphere is falling steadily at terminal velocity with no acceleration, which is why we're able to use the measurement only of the distance fallen and the time it takes to fall to infer the terminal velocity. And clear. 35.06 seconds.
So our second part of the experiment consists of dropping a number of steel balls, spheres, into the glycerin. So this time I'm going to measure it. This one is a smaller one. And I'm measuring here 3.59. Okay, so we can repeat the experiments. I'm going to close the gate, dump the sphere, has settled at the gate, and let's time it.
14.47 seconds.
All right, so now we have different materials, different geometries that are traveling at different terminal speeds, and that will give us enough information to complete our experiment. In a perfect world, this would be all we need, but because we're not in a perfect world where the measurements have some level of uncertainty, we are going to repeat this experiment 10 times with the Teflon balls and another 10 times with the steel balls.
And this collection of 10 independent trials with 2 different materials will give us a significant enough sample that we can draw some statistical inferences about how precise or certain we are about the measurements that we obtain.
All right, so we're back. We conducted our experiment and we collected the data that we needed to determine the density and viscosity of our fluid.
That's right. So let's remind ourselves of the data reduction equations that we left off on before the experiment, shown here, which allow us to infer the fluid density and kinematic viscosity of the test fluid by measuring the diameters, terminal velocities, and solid densities of 2 different types of sphere. Now, those of you paying attention may notice that we have these terminal velocities in here, and ask yourself when those were measured. The reality is they never were measured directly. What we did measure was the distance between the starting and stopping positions of the spheres, as well as the time it took for each sphere to traverse that distance. The length over that time gives us the terminal velocity. So to make things a little easier, why don't we swap these terminal velocities out for that ratio of length to time, which leaves us with the final data reduction equations.
So each one of these equations is going to give us an estimate of the viscosity of the fluid and the density of the fluid for every measurement of time that the sphere drop over the fluid on a distance lambda and for a particular diameter. So essentially, every pair of experiments where we dump a Teflon ball and steel ball gives us an estimate of these 2 variables.
That's right. And you may notice that we don't have subscripts on the diameter, the time, or the solid density over here. That's because once you've solved the fluid density, regardless of which sphere you choose, the Teflon or the steel, the second equation will give you the same result. So recall that we conducted 10 trials for each of the 2 spheres. And it's beneficial to lay out your results as well as your calculations in a table like this, where we have the diameter and the time for the Teflon spheres for trials 1 through 10, the same for the steel spheres, and carrying across each one of these trials then allows us to get a different estimate of the fluid density and fluid kinematic viscosity. We can then consider the amount of variability between our trials by looking at the average as well as the standard deviation, which leads into this idea of uncertainty. So we need to think about what the sources of uncertainty in our experiment are.
Right. So there are a number of sources of uncertainty that will let us determine or not the properties of the fluid. One I can think of is the length, the drop length that we measure. You know, we used a good ruler, but there is a limit on the precision of the measurements that we can do. So that's one.
Another is the timing with the stopwatch. The stopwatch itself rounds time to the nearest hundredth of a second, so there's some rounding error present in there. And we may also concern ourselves with the possible error in the measurement of the sphere diameters. We used a very, very nice set of calipers, but we saw different results each time we measured those.
Yeah, so those are uncertainties that are introduced in our measurements because of the instruments themselves. But because we were measuring time, there is a human error that gets introduced. You know, we have different reaction times. We might not stop the watch exactly when we want to, and that introduces a random error. So let's see how those errors would propagate into our estimate of viscosity and density.
So let's think first about the bias error. Recall that the bias error is error that may always be present and isn't random in nature, isn't attributed to us. So the source of bias errors in this experiment include, as we just said, the measurement of the distance fallen by each sphere, the time it took each sphere to fall, as well as the diameter of each sphere.
The coefficients in this equation get calculated using our reduction formulas. And in a sense, they tell us how important an error in the diameter, an error in the time that we measure, an error in the diameter for the second sphere, and the time that we took for that sphere to drop, those all communicated, add together, and communicate and translate into the total precision error associated to our measurement of density, and equally on the error associated on the viscosity.
So without going into too much detail, the steps to take here to estimate the bias error in each of our final two quantities are, first, to estimate the bias limit for each of our distinctive measurements, which will usually take to be half the minimum resolution of that instrument. Plug those in for B, and then calculate the sensitivity coefficients theta using the data reduction equations.
To arrive to this equation, we gave our students a full lecture on measurement uncertainty, so they should be familiar with the equation itself.
Now let's talk about precision.
Yep. So these are the types of errors that are induced, like I said, by human error, by conditions of using the instruments themselves, and time becomes here kind of the key that introduces that uncertainty. We repeated that experiment 10 times, so we can use the central limit theorem to create a bound on how precise are the measurements that we are making for the density of the fluid and the viscosity. So in this case, we can use the scatter in the data. We can calculate the standard deviation associated to our measurements, our estimates of density, the standard deviation associated to the to the estimates of viscosity, and create a bound for how big this precision is on our estimated variables.
Now you'll notice we didn't use any propagation equations here. This is simply because we have two options to estimate precision. We can look at the precision limits of each of our individual measurements, and just like with the bias limit, propagate those through our data reduction equations. But in this case, since we have independent estimates of density and viscosity, 10 each, then we have the sample we need to look at the scatter and the end results directly. So we can combine the precision and the bias limits into a total uncertainty by taking the Euclidean norm of B and P for the density and the viscosity to arrive at our 95% confidence interval half-widths. So once this is done, we need to think about how we analyze the data and possibly report it. So the easiest way to present your data or to consolidate it would be to report the mean, the sample standard deviation, the estimated bias limit and precision limit, as well as the total uncertainty for each of the two estimated parameters of our fluid.
So with that in hand, our estimate of the value of viscosity, that's essentially going to give us a bound on the error that we can make. If you remember, one of the variables that we measured during the experiment was the temperature of the fluid and the temperature of the room, and we said that the properties of the fluid were dependent on the temperature of the room. So in this case, this chart shows how the glycerin that we use changes density as a function of temperature.
And so the black line here is data supplied from a chemical manufacturer for a typical sample of glycerin. And ideally, when we plot our own data, even if it doesn't fall directly on this line, by rigorously treating the uncertainty, our error bars, which are plus minus one value of u, should enclose that line, showing us that if it is off, at least we know why.
Mm-hmm. Same thing for the kinematic viscosity that we measure here. We have manufacturer supplied table where we know what the density associated to the viscosity associated to those different temperatures are. Once again, our estimate of the viscosity is a little bit off, but the bound of our error bars falls within the expected value for that quantity.
So that wraps up our analysis of the experimental data for the sphere falling through glycerin. Hopefully that's been informative, and if you have further questions about it, feel free to email myself or Professor Mantilla, and we'll see you at the next lab.
See you at the next lab.